In this chapter, students will identify and generate equivalent expressions and use variables to represent numbers. Expressions are building blocks for working with equations and functions. Students have been writing numerical expressions since kindergarten. A mathematical expression expresses calculations with numbers. For example, 4 plus 3, or 3 times x, or 2 plus 3 in parentheses times 3. In 5th grade, students used exponents with a base of 10. For example, 10 to the second power. In 6th grade, students will start to incorporate whole number exponents into numerical expressions. For example, when describing a square that has equal lengths of 5 feet, students will see this as an area of 25 square feet. An exponent is the number that identifies the power to which the base is being raised. It represents the number of times the base is represented as a factor. For example, let's look at 10 to the third power. The base is 10, the exponent is 3, and the power is 1,000. There can be some confusion when it comes to discussing exponents. In this example, the 10 is the base and the 3 is the exponent. It can be read as 10 to the third power or 10 raised to the third power. The 3 identifies the power the base is being raised to. Oftentimes, the exponent is referred to as the power, when in fact, the product itself is the power. It can be thought of that we are raising the number 10 to a power, changing it into a more powerful form. Students will write and evaluate expressions with exponents without variables to begin with. For example, let's evaluate the expression 4 squared plus 2 times 5. The order of operations states to start with the exponent first. The expression now reads 16 plus 2 times 5. Next we multiply 2 times 5. The expression now reads 16 plus 10, which is 26. Next, students will read, write, and evaluate expressions with variables. When variables are used in expressions, the expression is referred to as an algebraic expression. For example, let's look at these trays of cookies. There are B amounts in the first 3 trays and A amounts on the second 2 trays. The expression to represent the total quantity of cookies on all 5 trays could be B plus B plus B plus A, or 3 times B plus 2 times A. Then students will identify parts of an expression using the correct mathematical terms of coefficient, variable, constant, and term, as seen here with the expression 6 times r plus 3. Next, students will evaluate expressions from formulas, such as the formula for the perimeter of a rectangle. The formula is 2 times length plus 2 times width, which means the length and width are both doubled and then added together. After students have had experience with expressions with variables, they will move on to working with equivalent expressions. They will begin by using the properties of operations to generate equivalent expressions. For example, let's examine the expression 24x plus 18y. This expression can be rewritten by finding common factors using the distributive property as 6 times 4x plus 3y in parentheses. Students will then identify when 2 expressions are equivalent when a value is substituted for the variable. Let's evaluate the expressions 2 times v plus 3 and 3 times v plus 2 when v equals 5. The first expression would be 2 times 5 plus 3, which is 10 plus 3 to equal 13. And the second expression would be 3 times 5 plus 2, which is 15 plus 2, which equals 17. The 2 expressions are not equivalent because doubling a number and adding 3 will yield an answer smaller than if the number were tripled and 2 was added. In this chapter, students identify and generate equivalent expressions and use variables to represent numbers. Expressions are the foundation of algebra. Students need to take the time to generate and develop expressions to represent given mathematical situations. Students also need the time to communicate and collaborate in order to have a firm foundation.